Okay, so I think I should get started. So my name is Wesley, and today I'll be talking about rejection sampling for off-policy learning. So here's the outline of the talk. I'll first talk a bit about doing TD updates off-policy. Then I'll review importance sampling, and then introduce rejection sampling, show some experiments comparing both, and then I'll talk about a different algorithm called rejection control and show a couple more experiments. So before I continue, I'll just say a few words about why I think off-policy learning is important. And I think Rich made a good point in his talk where he said basically an intelligent agent should be able to learn about many things at once. And one way to do that is to be able to learn about things that you didn't do from the things that you did do. And that's basically what off-policy learning is. So in reinforcement learning, I'll be considering the policy evaluation case. So we want to learn the value function vpi for target policy pi, but we can only use a different policy, mu. So here's our expected TD0 update. So W is a parameter vector, alpha is a step size, and then you have an expectation over the TD error delta t times the feature. And this expectation is over all the stochasticity. So this is the stationary distribution that picks the states, the policy, and the transition dynamics. So we want to get a sample of this expectation, but we behave according to mu, and this expectation is according to pi. So to do this, we can use a couple of techniques. So the first is importance sampling. So I'll go back to just the regular statistics framework. So we consider a random variable x, and it has some target distribution p of x. And we are only able to sample from another distribution, the proposal distribution q of x. But we want to estimate some expectation with respect to p. Now, many of you have probably seen this already, but here's how importance sampling is derived. Well, you just write down what the expectation is, multiply and divide by q of x, and then you can just interpret that as an expectation with respect to q, except you introduce this ratio p of x divided by q of x, and we'll call that rho. So once you have this expectation, you can just sample a bunch of x's from q of x and compute this quantity and take the regular sample average. So that's great, but what happens when q of x and p of x don't match? Well, so let's just say that the blue distribution is our proposal distribution q of x, and red is the target distribution p of x. So when we sample from this, most of our samples will lie under the area, under this area here, where the proposal distribution has high density. But there, the target distribution has low density. So the ratio rho of x will be very small. So those samples won't contribute much. But from time to time, you might have a low probability event that happens, and you'll sample something around here, according to q of x. And that sample will have a gigantic importance sampling ratio. So there's very high variance in your estimate, which is not good. And it's even worse when we are doing reinforcement learning, because we want to do an update of this form. So alpha times rho of t times the TD error and feature vector. And since we want to find the parameters that achieve some minimum error, well, if you just have one very large update, it could throw off your parameters very badly. And this would undo all your previous work at finding the minimum. OK, so importance sampling can be bad because of this problem. So what's an alternative? Well, another textbook example of a sampling algorithm that can do this type of thing is rejection sampling. So the problem is framed like this. You want to sample from the target distribution p of x, but you can only sample from a different distribution q of x. And here's the rejection sampling algorithm. It's really simple. you first need to find a bound L such that L times Q of x is greater than P of x for all x. Then you generate a sample xi from Q of x and a uniform random variable. Then you just simply check if U is less than that ratio, and if it is, then you take that sample and accept it, and if not, you reject it and you just throw it away. So if you wanted to generate, let's say, n samples from the target distribution, P of x, you might need to repeat this many times, because every time you reject something, you just throw it away. And it turns out that the probability of accepting a sample is about 1 over L. So you want L to be very small so that you'll accept many of your samples. So I won't go through the proof of why that works, but maybe I can give some intuition as to why this works at all. So first, let's just consider the red, which is your target distribution. And let's just ignore the rest for now. So, so this is a probability density function. And I claim, I guess, or it's kind of intuitive, that if you were able to sample uniformly under that curve, and you just considered, so maybe you would sample points anywhere under that curve. And then you just consider what x value does that those samples have. Then those samples would come from the correct distribution, P of x. And the reason why is basically, well, if you're sampling uniformly under here, you have, and then you consider, well, what's the probability that you sample from a strip somewhere? Well, that probability is exactly the integral of P of x between those 2 points. And that's, by definition, what the correct probability is. So what does rejection sampling do? It generates a bunch of x's according to Q of x, and then U. So on line 2, if we look at the inequality, you can rewrite that as U times LQ of xi, less than P of xi. So what is U times LQ of xi? That's basically a point on this line. So it's underneath LQ of xi, which is the blue curve. Oh yeah, I should have mentioned that. But yes, and then basically the condition is if the point you sample, which is on that line, is underneath the red curve, then you accept it. If not, then you reject it. So how does that relate to what I said before? Well, essentially what rejection sampling does is it samples uniformly underneath the blue curve, but it only accepts those that are underneath the red curve. So in that way, you can generate samples from the right distribution. So now you see what the problem is that what's this area between the red and the blue? Well, that's the rejection area. So if that area is very large, well, this procedure will be inefficient, and you'll have to reject a lot of samples. OK, so how do we use rejection sampling for TD updates? Well, recall that we want to sample from this expectation. So at time t, we receive this transition st, at, rt plus 1, st plus 1. And from this, we can compute a sample of delta t xt. So easy way to use rejection sampling is you just check the previous condition where, well, OK. So the way you use it is you say your target distribution is now your target policy, pi, and your proposal distribution is now your behavior policy, mu. And then you can use the same algorithm as before to decide whether you should reject or accept this sample. And if you do accept it, you do an update. If you don't accept it, you don't do the update. So what are some possible advantages? Well, the first is it doesn't require the importance sampling ratios. So this could make, this could make learning possibly more stable and have less variance. And 2, it might be easier to tune step sizes because the accepted samples look as if they were actually generated from the target policy. So I would imagine that a good step size here would be a good one for the target policy. But on the other hand, compared to importance sampling, usually you need to be careful with the step size so that the largest importance sampling ratio times your step size isn't too big. But here, you wouldn't need to care about that. So that's kind of related to the first point. And then finally, the third point is that you might be a bit more computationally efficient because whenever you reject a sample, you don't have to do an update. And let's say you have a big neural network or something, a parameter update is really expensive compared to the cost of just sampling the uniform random variable and sampling in action. So let's just see how it does. So I have a couple of experiments. So it's a really simple environment, just a one-way corridor. You start on one end, and no matter what you do in each state, you have two actions. You always move right, but one of the action gives you a +1, and the other action gives you a -1. So target policy just chooses the good action 99% of the time, and then I vary the behavior policy with choosing the good action 10% of the time, 1% of the time, or 0.1% of the time. I also use function approximation to make it more difficult, because if you just use a tabular representation, then both methods do really well. So I just took this simple representation where I just generate a random vector of length 5, and each entry is just a uniform random variable. So here's how they do. On the left, you have the learning curve. So I chose the hyperparameter that minimized the area under the curve. Yeah. And then on the right, you have the step size sensitivity curve for the same thing, with the same thing on the y-axis. So what we can see is that, well, they kind of do about the same, actually, in terms of the area under the curve. And on the left, actually, the rejection sampling seems to have less variance overall. So that's promising. What about the other settings? So the other one was 1%, and the one at the top is 10%, and the one at the bottom is 0.1%. So with 10%, it seems like both algorithms do very well. Like if you look at the learning curve, they, especially importance sampling, gets almost to 0. And then something weird is going on with the sensitivity, which I'm not too sure why yet. But yeah, aside from that, then for the 0.1%, then they both do comparably again. So any questions at this point? Yeah?
These models assume you have the two distributions, P of x and Q of x. Where do you get them?
Right. So in policy evaluation, we usually think of both policies as fixed. So they're just given to us. Okay. Yeah, for the setting.
You don't have to estimate them. You don't have to estimate them.
Yeah. Yes?
So for the function approximation, did you do a random assignment of the linear or the binary representation for each trial separately? And if so, did you check for aliasing? Do you know, is it still a one-to-one mapping, or was there aliasing or lack of coverage?
Right. So I generated a fixed set of random features, and then I used the same set for all the runs. Yeah. And actually, so from the top left, we see that the error approaches 0. So we can see that it's definitely possible to get a really accurate value function with those features, but it just can't do it in some of the other cases. Yes?
There are 5 states in the problem?
Yes.
The feature vector was length 5?
Yeah. Yeah.
Are you correcting the distribution of returns, or is it possible to correct the state distributions?
You mean like the stationary distribution, or?
Yeah.
Yeah. So in this case, yeah. So this environment was designed in such a way that the stationary distribution was the same for both policies. Since you always move to the next state, no matter what you do, you always have the same frequency in each state. Yeah. Yes.
So for the lower left graph, it seems like the difference in the policies is very large there. So you'd expect that the importance sampling rate should be really high, and you would have a really high variance. So why do you know why the rejection sampling method, which seems like it would have lower variance, do you know why it has such large error bars as well?
Right. I think it's because, well, if you look at the right side, basically you have to pick like 1,000-fold less smaller step size for importance sampling. And I think that kind of counteracts the importance sampling ratio. Yeah.
What did you use for L in your experiments?
Right. So for L, I just used the smallest L possible for that would still give an upper bound. And that means that it's actually equal to the largest importance sampling ratio. Yeah. Yes?
Sorry, I just have a question. So if you decide to reject that one-step transition, what happens? If that just does not...
Yeah, we just forget about it.
Okay, so that doesn't go into the estimates.
No.
Okay, but then what happens afterwards? Do you follow that state, the next state in action? Or
Yes.
do you-
Yeah.
Okay.
So I only decide whether I do an update or not with this. The actual actions taken are like independent in a sense. Yeah. Yeah.
So in the label of the curve, the upper right one doesn't have like 0.001. The upper lower one has. What does that mean?
Oh yeah. I think I just. Okay, yeah. It doesn't mean anything. It's just this is just importance sampling and rejection sampling. I just forgot to change this to just IS and RS. But yeah, it doesn't change anything.
I mean, which linear rate it reflects on the left figure?
The left figure is the best one. So the one that achieves the minimum on this graph.
Oh, so these two curves have different two learning rates.
You mean like the top and the bottom one?
I mean, the two curves in the upper.
Oh yes, that's right. Yeah. So for example, rejection sampling would pick something here, but importance sampling would pick something much smaller. Yeah. Yeah.
Do you think if we had multi-step returns instead, the difference would be exactly limited because of products of importance sampling?
Maybe. I'm not exactly sure how I would use rejection sampling in that case, because you would have to. Yeah, I guess you could still do it. So I'm not sure. I haven't thought about it. Yeah. Yeah.
Some samples you reject and then you don't do the update.
Yeah.
Some samples you don't reject, but those samples are still coming from the behavior policy.
Right.
How come you don't need an importance sampling ratio to correct the TD error for those samples that you do not reject?
So basically it corrects it through the number of times you reject. It's like you'll reject it the right number of times so that the proportion of accepted samples will be exactly equal to the proportion you would have had under the target policy.
And that's because of the generation of U to decide?
Yes, yeah. Yeah, Nico.
So even though you're rejecting samples, it looks like you're learning at the same rate.
Right, yeah.
You have some intuition as to why that is.
Well, you can just take bigger step sizes, I guess. I'm not, apart from that, I don't really know why. Okay, so I'll move on. So what I thought was, okay, this is great, but can we develop a new algorithm that can go between importance sampling and rejection sampling? And I guess from the title, well, the answer is yes, and it's called Rejection Control. And basically, this is the algorithm. So I won't go into detail how it works, but there's two key things. First thing is you don't need an actual upper bound on P of x. So before you needed to pick an L such that LQ of x was bigger than P of x everywhere. But here you can give any L. And but to compensate for this, sometimes you will need to multiply by something like an importance sampling ratio. Yes. And it turns out that if you pick L very small, then this behaves exactly like importance sampling. And if you pick it very large, it's exactly rejection sampling. Okay, but choosing L can be kind of complicated and not intuitive. So alternatively, you can choose a bound B on the size of the importance sampling ratios and solve for the corresponding L. So it turns out that there's this trade-off between the acceptance probability and your bound. So here's an example. So this is from the one-way corridor where the target policy takes the good action 99% of the time, but the behavior policy takes it 1% of the time. So your maximum importance sampling ratio is 100. So if you look up here, basically if you accept all the time, then sometimes you'll have an importance sampling ratio of 100, which is what importance sampling would do. But on the other hand, if you want to have a bound of 1, which is basically no importance sampling ratio, then you only accept like about 1 in 100, which is what rejection sampling does. But you can also tune B to pick some number between them, and it gives you a nice linear curve that trades off both. So how does this do? Well, I made up just a slightly more complicated environment. And this is it's a grid world that wraps around the edges. So if you move east from here, you just end up on the other end. The target policy goes north a lot with 70% chance and 10% the rest. And the behavior policy goes east a lot and south. But it doesn't go north a lot. So sometimes you'll have high importance sampling ratios. Yeah. And you just get +1 if you leave this state and -1 if you leave that state. So how does that do? Yeah. Oh, yeah.
Observation space and state representation?
Oh, yes. So the state representation is, OK, let me go back. So I have, for each of these tiles, I've placed kind of like a detector that is 1 if the agent is within one space of it or not. So you have 36 of these. And if the agent is within one of each of these, the corresponding entry in the feature vector is 1. Yeah, if not, it's 0. So here are the learning curves. So actually, a lot of the algorithms do kind of the same. Oh, yeah. And also, as another baseline, I introduced a cap, which is importance sampling, but you just cap the ratio to a certain amount. So if it exceeds like whatever the bound is, it just becomes that bound. So that method is biased, unlike the other 3. So on the left, we see that, well, except for rejection sampling, the other 3 do kind of the same at their best settings. But from the sensitivity curve, we see that actually rejection control can do better over a higher range of step sizes. Yeah. OK, so let's look at, so what about the sensitivity to the bound, though? So it turns out that, so for importance sampling and rejection sampling, they don't have a bound. So I just include them there as just for comparison. But rejection control, you see, is pretty insensitive to the bound, actually, compared to cap. Here's a 3D plot. So these are just 2 perspectives on the same plot. And just so that you can see the interaction between the step size and the bound. And basically, it's like a valley that kind of goes diagonally a bit. But in the end, the minimum is about the same for every setting of the bound. So what that tells me is that you can set the bound pretty low and not do do fewer updates and still do as well as importance sampling, basically. So in conclusion, rejection sampling seems to be comparable to importance sampling, slightly worse in some cases, but it has other benefits. And if you're not satisfied with that, you can always use rejection control, which lets you trade off more finely between the importance sampling ratios and the acceptance probability. And finally, looking into other sampling techniques, could provide some inspiration for new off-policy techniques. Thanks. Any questions? Yeah, Nico.
So this is super cool. Have you thought about doing experiments in stochastic worlds where like the transitions or rewards are stochastic? Because if you're doing updates only infrequently, you might have a big impact compared to important sampling.
Right.
The world is stochastic in some way.
Yeah, I haven't tried that, but yeah, I see like maybe it would be higher variance due to rejecting a lot of the updates. Yeah. Matt.
Yeah, do you have any idea like how your method would compare to something like weighted importance sampling?
Weighted importance sampling. I'm not sure. Yeah, I know there was this paper where, because you can't naively do weighted importance sampling in reinforcement learning, but apparently there's this way to do it online.
Yeah, I
and
think it's like a 2015 paper or something.
Right.
Yeah.
I think weighted importance sampling might be able to do better, I think, yeah. Since it makes use of every sample, but also maybe doesn't have that much variance. Yeah, Lily.
Shouldn't the AO is always greater than 1 because your AO times your proposal distribution, so it can cover the target distribution.
Yes, for rejection sampling, yes.
Yeah, so it should be always greater than 1 instead of any positive.
Okay, so for rejection control, you can pick any positive number because you don't need an upper bound. That was the key. You don't actually need. Oops. So. Yeah, so here you could use any L, but the cost of that is that sometimes you need to use importance sampling ratios to correct for not having an upper bound on the P of X. But for regular rejection sampling, you do L is always greater than 1, yeah.
So when I think about rejection sampling, I'm thinking that it will be much less sample efficient than importance sampling. But from our experiments, it seems like these two methods are comparable in terms of number of samples.
Right. Yeah, I found that a bit surprising too. But I think it has to do with the thing about step sizes. So if importance sampling, for it to work, you kind of have to make the step size quite small sometimes to account for the worst case scenario of having a very large importance sampling ratio. So that's why maybe it's not as sample efficient as it might seem at first, yeah. Yes?
So the value function you were learning was linear in the spaces you described?
So do you mean like, can it be perfectly represented by the
No,
features?
literally, did you do a linear update for the learning?
Linear in terms of?
Were you learning a vector of weights of the same length as the features?
Oh, yes, yes.
And was there a bias term?
No bias term, yeah. Any other questions? All right, thanks.